Welcome to the Microeconomic Theory 2 class for 16th April. We are continuing with our discussion of games of incomplete information. Today we will talk about various applications of this concept and Bayes-Nash equilibrium. And the first application is market for lemons, something that we had done before but under the competitive market framework, non-game theoretic approach. Okay, so today we will sort of revisit the same model, but we will apply a game theoretic structure to this concept of market for lemons, to this application of market for lemons, and try to understand how game theory also helps us analyze this situation in different ways. Market for lemons is a nice context to apply Bayes-Nash equilibrium and the concepts of incomplete information games, because it is a context where one side suffers from a lack of information about the other side of the market. So as the context of the market for lemons goes, we are interested in understanding trades in used car markets, right? And in this context, the cars can be of different qualities, which is unobservable to the buyer but is observable to the seller. Okay, so the quality of the car is an important information that sort of matters to the payoff of the buyer, which the buyer doesn't have, and hence it's a model of incomplete information. And it is strategic because the decisions or the strategies of trading by the seller may have a bearing of different high or low quality cars, may have different payoff consequences for the buyer, and therefore the buyer has to choose its strategy of whether to trade the car or not accordingly, and hence it's a strategic environment. Okay, so let's try to formalize. So we are interested in, so we model the trading decisions between a pair of buyer and seller of a used car. Okay, and what we are assuming, so for simplicity we assume that used car can be one of two qualities: high, denoted by H, or low, denoted by L. Right, so quality can be either high or low, and it matters for the payoffs of the buyers and the sellers. So what are the payoff metrics? So suppose in order to decide the payoff metrics, you have to specify a price. So suppose the ongoing price of a used car is P. Okay, so suppose the price of the car is P, and this is the payoff metrics of the buyer and the seller. So let me write down the strategies of the buyer is whether to trade or not for the buyer, and for the seller is also whether to trade or not. Now here I am modeling the seller of the high type. So remember the high types are called peaches, and the low types, the bad quality cars, are called lemons. So hence the title of the model, Market for Lemons. So to sort of to identify the strategies for the peach guys and the lemon guys separately, we will tag the sellers strategies by the type, right? So here the idea is that peach, the high quality car, and lemon, the low quality car, are types of seller, because these are the different types of sellers. So as we defined types in the previous class, so these are the different types of cars that a seller can sell, and which is unobservable to the buyer, and hence these are the types of the seller. So we associate the car to be sold with the seller. Okay, so if both say T, i.e. both say trade, only then trade takes place, only then the seller is able to sell the car to the buyer. If any of them says N, no trade, then there is no trade. Okay, so if a peach car is traded, then the payoff to the buyer is 3000 minus P, and the seller's payoff is P. Let me write the seller's N bit separately. And okay, so the 3000 is the payoff to the buyer for a car which is of high quality. Okay, now buyer obviously doesn't know whether it's high or low quality at the time of saying trade or no trade, but I'll come to that later. But in case he purchases a high type, a peach car, then the payoff is 3000. He pays price P, so the payoff is 3000 minus P. Seller gets the price P. Okay, if the car is not traded, then obviously the buyer gets 0. The seller gets to keep the car, and the seller's payoff of the car is 2000. So what does this mean? So for the seller, the peach quality car is worth 2000 to him. Okay, and if the same car is bought by the buyer values it at 3000. Okay, so basically it means that buyer's valuation of the car is bigger than the seller's valuation, so there is benefit for trading, right? Efficiency requires that the seller should sell the car to the buyer, because buyer gets a higher payoff from the car than the seller. Okay, now in all other cases there is no trade, so the payoff is same, so it's 0 2000 and 0 2000. Okay, so this is the payoff matrix in case the car is of high quality, if it's of quality peach. If it is of quality lemon, then we have a different payoff matrix. So let me write down that. So it's trade, no trade by the buyer, and trade, no trade by the seller, where the seller is of type L. L means lemon. Okay, so again, when both says trade, only then trade takes place, in which case the buyer's payoff now in buying a lemon car is 1000 minus P, and seller's payoff is P. Okay, so notice the payoff of buyer for a used car is lower when the car is of low quality. Okay, so it's instead of 3000, it's 1000. Okay, and in case there is no trade, so if anybody says no trade, then there is no trade, in which case the payoff is to the buyer 0, and for the seller is also 0. Okay, so now notice the lemon quality car is worth 0 to the seller and is worth 1000 to the buyer. So again, there is benefit of value in trading, because the buyer's valuation is greater than the seller's valuation. Okay, so in all other cells it will be 0, 0, because there is no trade. Okay, Now let me write down the nature move first. So the nature decides whether the card is of high quality, low quality. I have to decide, I have to specify the probability distribution over the car being quality peach and the car being quality lemon. So we will model it as the nature choosing one of the two qualities with certain probabilities. So the nature chooses the car of quality peach with probability q and quality lemon with probability 1 minus q. Okay, so with probability q it is peach, and with probability 1 minus q it's lemon. Okay, so this is the sort of the overall structure of the game. Now given this structure, we have to find out what are the possible equilibrium, Bayes-Nash equilibrium strategies of the two players. Now notice, because Saylor has two types, Saylor's strategy will be type contingent. Remember the definition of strategy in, as we discussed in the previous class, for every type, for every node basically, the seller has to make a choice about whether to trade or not trade the car, and therefore since the seller knows the type of the car, so for each type the seller has to specify an action. So seller's strategy is type contingent. Okay, so basically seller has 4 strategies. It can say I'm going to trade if it's peach, I'm going to not trade if it's lemon, I'm going to trade if it's peach, I'm going to trade if it's lemon, and so on. So it has sort of 4 combinations. Okay, so it's buyer's strategy here is only either to trade or not, because buyer doesn't know the quality about the car. Buyer only knows the probability distribution q1 minus q across the 2 types, and therefore buyer has to say whether it wants to trade or not. Okay, now initially, since buyer doesn't know anything about the quality, buyer believes that the seller has a quality peach car with probability q, and it has the lemon car with probability 1 minus q. However, in equilibrium, buyer can use seller's strategy to sort of update the belief. So suppose we want to understand, is there a strategy where only lemon is traded? Okay, so we try to check if there is an equilibrium where only lemons are traded. Okay, now so what kind of strategy, so what kind of strategy in equilibrium would give rise to this kind of an outcome where only lemon would be traded? So suppose the strategy that we want to see is in equilibrium we get or not is the case where the seller says no trade for the peach and trade for the lemon. Okay, so the seller of the peach type says no trade, and the seller of the lemon type says trade, and buyer says trade. Okay, so we want to check, is this Bayes-Nash equilibrium? Okay, so this will be the case where only lemons are traded, right? Because buyer is saying trade and only the lemon types are saying trade from the seller side, not the peach type. So only when the cars are lemon, when both sides say trade, and only lemons end up getting traded. Okay, so now can this be an equilibrium? For this, let me find out what are the payoffs. Now notice that given this strategy of the seller NP and TL, buyer knows that in case it is getting traded, buyer is getting the lemons, right? Buyer no longer believes, if this is the equilibrium, that if this is an equilibrium, in equilibrium only lemons are going to be traded, and buyer knows this, right? buyer is in equilibrium, buyer is aware of the equilibrium strategy of the opponent, of the seller. Okay, so given the equilibrium strategy, so given the strategy of seller, the buyer updates his belief about the quality of car. Okay, now what is the updating? So before these strategies were decided, buyer believed that with probability q it is peach and probability 1 minus q it is lemon. But given the strategy of the seller that I have specified here, buyer knows that in equilibrium if there is a trade it is of quality lemon. So buyer then updates that with probability 1 it is lemon and with probability 0 it is peach. Okay, so buyer now believes that if seller trades, it will be a lemon. And that is because of this given strategy that I've specified. For some other strategy, the belief will be something else. So basically the buyer uses the strategy of the seller to update his belief about the information that he is lacking. Okay, so basically just to be more specific, buyer believes that it will be a lemon with probability 1. Okay, right? So so now notice that this updating process, given the strategy of the opponent, this actually uses Bayes rule. So this is a case where we are actually using Bayes rule, even though it's sort of a very trivial use of Bayes rule, where the strategy already reveals for sure the type of the car that is being sold. But still it is an Bayesian update. Okay, we are using Bayes rule to update. Bayes rule will actually, if you apply Bayes rule here, given the strategy and the prior belief of q1 minus q, you will find that the updated belief will be probability 1 using Bayes rule. Oh, right. We will see a sort of more general application of Bayes rule in Bayes-Nash equilibrium in a separate example. But just to sort of specify, this is something where we are indeed using Bayes rule, okay, implicitly. So now that the buyer in this strategy, buyer knows that it is a lemon, then buyer is ready to trade. So buyer would optimally buyer would optimally choose trade if 1000 minus p is bigger than 0, right? Because buyer knows that that it is of quality lemon, so therefore with probability 1, so therefore his expected payoff is actually 1000 minus p. He knows that he expects a lemon, and so he'll trade only if this is positive. Okay, which means that p must be less than 1000. Okay, knowing that p, so basically buyer would optimally choose trade. So buyer will indeed go through with the trade only if p is below 1000. Suppose p is indeed below 1000 and hence buyer is choosing to trade. Is it seller's best response to choose this strategy. We want to find out whether this is an equilibrium or not. We just specified it, right? We have to verify whether this is indeed an equilibrium. That's the question I have asked. So the first thing we have tested so far is that buyer will say trade only if P is 1000, less than 1000. Okay, so suppose that is the case. So suppose P is less than 1000, buyer is optimally saying trade given seller strategy. Is seller strategy that's the thing that I've specified as the best response? So question is, so basically then the lemon seller would choose trade if P is bigger than 0, right? If I go back to the matrix, you see lemon seller gets 0 payoff if he says no. He gets payoff P if he says trade. Okay, so therefore lemon seller would say trade if P is bigger than equal to 0. Okay, so suppose price is always positive, so this is satisfied. Okay, the peach seller would choose no trade because that's the strategy that I have specified if P is less than 2000. Right? Again, let's go back to the matrix. Let's look at the peach seller. The peach seller, if he keeps the car, the car is worth 2000 to him, so he'll not sell if the price is below 2000. Okay, so now therefore if price is below 1000, then buyer saying trade and seller of type peach saying no trade and the type lemon saying trade is indeed a Bayes-Nash equilibrium. Okay, oops. So this calculation, this analysis shows that it is possible in equilibrium that only lemons are going to be traded. This is an inefficient outcome, right? Because we know that even for the peach high quality cars, it is efficient to trade because buyer values the high quality car more than the seller values it. But we see that there is an equilibrium, Bayes-Nash equilibrium, where only lemons owners are ready to sell, ready to trade, but the peach owners are not. Sorry, here I've written it incorrectly. It should be lemon, right? And this will happen when price is low. So when price is below 1000, we see that only lemons are getting traded. Okay. Question is there an efficient equilibrium? So is there a case where all parties are ready to trade? Let me ask then that question. So we have observed that inefficient outcome can arise in Bayes-Nash equilibrium of the game when price is below 1000. Okay. We now ask, is there a Bayes-Nash equilibrium which is efficient, i.e. is there an equilibrium of the following kind? Where buyer says trade and sellers of both type, peach and lemon, also says trade. So is this an equilibrium? Or under what condition would this be an equilibrium? So that's the question to ask. So because that's an efficient outcome where everybody is trading, so all the cars will be traded. Okay. So this is in the next video.